All right, let's talk about polarity. So ultimately we want to know, is a molecule polar? Okay, there's several steps though to get there. Okay, first of all, we have to be in the covalent bond world, non-metal to non-metal. We must be in the covalent bond world. We can't be in ionic bond because ionic substances have a charge and therefore they are charged, which is more than being just polar. So before we can say the yes or no, we have a few steps. So you'd be given a formula, and the first step would be to draw a 2D Lewis dot structure. Okay, that's where you have to determine the number of valence electrons that you have to work with. You usually have a central atom with some surrounding atoms, and then you have your 2D structure that you draw. So we've already done that in this class. Now, one of the things I want to mention is this, the next step. This is the geometries that the McMurray textbook uses. There are more than these. There's an image in your book that also shows the ball and stick format for some of the geometries. Okay, you need to be in the habit of, when you go on to step 2, which is determine the 3D geometry of the molecule, what you need to do is you need to say, okay, I need to know not just the name of that, but what it generally looks like in the three-dimensional world. For example, this on the far left is the most popular one that you would probably see, especially as you move on into organic chemistry and looking at biological molecules. That general shape where carbon is usually in the middle with 4 surrounding molecules, there's no lone pairs, is tetrahedral. And it's not just like a fat atom and a skinny bond and a fat atom and then skinny bond, fat atom. It's filled, there's matter present, and that's why this other option is what you have seen sometimes. That's the space filling model. And it may be easier to see in some of the smaller ones, like way over here. It's not just fat atom, skinny bond, fat atom. There's 2 spherical atoms bound together in a bond that we represent as a line, which is why in the ball and stick format you can see that line, whereas in this sort of space fill that's more true to reality, you don't even see the line because the atoms, that density where the electrons exist, the atoms take up so much space you can't see the connecting line. Okay, so you need to, once you have a Lewis dot structure, determine the geometry of the molecule, and that's just based on the amount of lone pairs on the central atom and the VSEPR theory model that we've already discussed in class. Okay, from there, I'm going to make a note. The next step is determine if individual bonds are polar. By polar, you're looking for electronegativity difference in, I'm going to put in quotes here, players on the bond. Okay, so if you have element A bound to element X, you're looking at what is the electronegativity of element A, what is the electronegativity of element X, and that is why you need to know electronegativity. Because remember, if, for example, if X is like one of those in the corner, the famous 5, so here's your periodic table, kind of ugly periodic table, the main part of the periodic table, okay, and this corner is F. Remember, the 5 in the corner, the famous 5, NOF, and then it's small CLBR. Those in the corner are the most electronegative. Remember, the trend follows this way. So if X is one of those say we'll just pick on fluorine, then we have a partial positive charge. That's not a full positive like potassium 1+. And then if A, for example, would be like carbon, or I'm sorry, not positive, I'm sorry, negative charge, partial negative charge, because by definition, electronegativity means I'm selfish, I want my electrons a little bit more, this bond a little bit more kind of uneven sharing than a nonpolar covalent bond. So if this were carbon, it would be a partial positive charge. And we draw it with that funky delta symbol. Now nobody wants to draw all this artwork below their bond, so they would just rehalve our A to X, and they would say this is the general positive region of the bond, and it points toward the general negative region of the bond. So if you have a completed structure, you would add up, you would look at each individual bond in this step 3 here, and you would write this arrow that is called a dipole moment. You would write that arrow, okay? You need to visualize that these arrows are adding up in the three-dimensional world, from whether you're thinking ball and stick model or the space film model, or if you actually like the images from the table 4.3 in the textbook. Okay? Then the last step is to determine if all dipole moments on the individual bonds result in the entire molecule being polar, or if they add up and, for example, based on the geometry, cancel each other out. So one example, a beautiful example of this canceling out. So let's go through CO2, okay? Let's actually go through it, and we already know it has double bonds, so we're not going to take our time on the Lewis structure. We're going to actually just do the Lewis structure quickly. Remember, carbon contributes 4 electrons, so that's kind of the, we'll go into examples here. Carbon contributes 4 electrons, oxygen has 6 valence electrons times 2 of them, times 1 of them. Okay, so I have 16 electrons to work with to build my structure, which is why carbon dioxide forms this Lewis dot structure that contains 2 double bonds, carbon in the center, and we have oxygen on the left and an oxygen on the right. Okay, so we've done number 1. To determine the geometry, you would just have to know this follows AX2 pattern we talked about in lecture, and say, okay, that's linear. So now on to step 3. Oxygen's one of the famous 5, so I'll actually put my little negative delta down there, positive delta by the carbon, and negative delta below the oxygen on the left. I'm actually going to draw my 2 dipole moment arrows above the molecule. So there's the one leading to the right. So this oxygen on the right is pulling on that double bond based on the fact that oxygen has a higher electronegativity than carbon, and specifically oxygen is one of those famous 5 in the corner. Okay? And then we have a dipole moment pulling with the exact same intensity to the left. This whole thing is linear. It's not bent in any way. So oxygen on the right is pulling just as hard as oxygen on the left, which means, to answer number 4, is the entire molecule polar? This is nonpolar because there is no net dipole. They don't add up, they actually cancel each other out in sort of a tug of war. Let's focus in on some tetrahedral examples, okay? So you may just want to draw CH4, okay? So CH4, I'm not even counting my electrons for the sake of time. CH4, you might draw it there. Two-dimensional world looks like a plus sign. But in reality, I'm going to pick on this hydrogen down here. We'll number them 1, 2, 3, and 4. This hydrogen, number 3, is coming out of the board at you. And this hydrogen, number 4, is fading away into the distance. That is, if you scroll back, this, I'll erase so you can see, this tetrahedral shape. okay? Because AX4, which is what this is, there's no lone pairs in the central carbon. This is AX4, so it's tetrahedral, okay? So it would be more accurate to draw it where anything coming out at you has this sort of bolded, it's a wedge that we fill in. I'm really exaggerating it, okay? So he's jumping out at you. That's what that bold wedge is supposed to be, and it's a wedge. That's what we call it. And that is hydrogen 3. Hydrogen 2 and hydrogen 1 are in the same plane as the carbon in the paper. And then this hydrogen 4 is kind of shaped like a wedge, but we sort of fade him off into the distance. This representation with the wedge that's solid and the wedge that is slashed, in some textbooks don't do the wedge that's slashed, they just do like a dotted line fading into the distance. The slash is what you'll see in more chemistry books, okay? My slash isn't even a very pretty triangle. That is trying to represent the tetrahedral shape that we see by this ball and stick format, okay? So if you were to draw, and now this has no net dipoles, but if you were to draw dipoles, you would need to account for the fact that they're all evenly spaced, but it's not just this plus sign shape that you see on the far left, okay? It's not just like a plus sign north, south, east, and west. So let's change out one of the hydrogens. Let's make it CH3, and we'll just pick on fluorine still, okay? So let's just make him going up to the top, and I am going to do my wedge so you're comfortable with seeing that. Oops, and the slash. Okay. Once again, no net dipole on the carbon to hydrogen bond, whereas the fluorine has negative, positive. Okay. So my individual arrow there is just for the individual bond. It may be easier for you to recognize the net overall molecule has a trend like that. So maybe you need to get in the habit of doing like a jumbo big arrow net like that, okay? Pulling that way. Since that's just one arrow pulling that way, one polar bond, we know that the entire molecule is polar. If we have CF4 and the whole thing, we're still tetrahedral, but the whole thing has a total of 4 dipole moments. I'm not going to draw my lone pairs on fluorine. It takes too long. Okay. We have poles going that way, poles going that way, pole going into the board, and a pole coming out. By pole, I mean the electronegativity pull of fluorine against carbon in that covalent bond. Okay? These are all evenly spaced. You might think if your Lewis dot structure looked more like the plus sign in the two-dimensional piece of paper, you might think, oh look, up and down, left and right cancel out just like carbon dioxide did, and therefore it's no net charge. And you would actually be correct. This whole thing totally cancels out because this angle is even among all of them. Fully cancels out. No net dipole. Okay? You cannot follow the pattern where, okay, two-dimensional and three-dimensional hold true, because depending on how you draw your Lewis dot structure, you could be wrong. For example, water. I'm running out of time. If you draw water wrong this way, it looks linear. If you're like, oh, it's a linear geometry, I have poles in, we cancel out nonpolar. But remember, water is bent, so the overall charge, I'm running out of time, the overall is going to be positive down here, the entire molecule. How did I solve that? I did the individual bonds, okay? Thank you, and hopefully that helps.